Literally at this exact second, our planet is under a constant, completely invisible bombardment. I know, it sounds like something straight out of a sci-fi movie, right? But it's an absolute, scientifically proven fact. There is this mysterious force from the deepest, darkest corners of outer space, and it's just raining down on us, day and night, entirely unseen. So, in today's explainer, we're gonna play Cosmic Detectives. We're tracking down exactly what this invisible phenomenon is, where it's coming from, and honestly, why it matters to every single one of us. To really wrap your head around the scale of this mystery, just think about the number 140. That is the exact number of invisible space particles falling onto your desk, or your kitchen table, or even your shoulders, every single second. Tick, tick, tick. That's hundreds of particles zooming down from the cosmos in the time it just took you to take a single breath. It's totally staggering to think about. But if they're everywhere, all the time, how on earth did we even figure out they were there? Let's look at discovering the invisible world, the history of radiation. Well, before we could look up to the stars to solve this, we had to learn how to see the invisible right here on Earth. The whole thing kicked off in 1896. A German physicist named W.C. Roentgen totally shocked the world by capturing an image of human bones using this new, crazy, penetrating force he called X-rays. And get this, that exact same year, French scientist A.H. Becquerel realized uranium was emitting mysterious rays that could expose photographic films straight through wrapping paper. No way, right? Then, between 1898 and 1911, Marie and Pierre Curie just blew the field wide open. They discovered radioactivity and radium, which was tens of thousands of times stronger than uranium. But here is where the story leaves Earth. Building on all that radiation research, Austrian physicist V.F. Hess eventually realized something wild. Some of these highly penetrating rays, they weren't coming from glowing rocks in the ground at all. They were coming from space. Moving on to what are cosmic rays, the invisible culprits. So what exactly is our prime suspect here? Just listen to this measurement. A single cosmic ray particle is incredibly, almost incomprehensibly tiny. We're talking 1 trillionth of 1 millimeter. I mean, that is vastly smaller than a virus. Because they're so unbelievably microscopic, they are completely invisible to the naked eye. You could literally be staring right at a massive shower of them and see absolutely nothing but thin air. And because they're that tiny and carry such intense penetrating power, they don't just stop when they hit a solid object. Cosmic rays get into everything. They pass straight through the ground, right through thick cement walls, through the roof over your head, and yeah, even right through your body, totally unnoticed. Indoors, outdoors, it really doesn't make a difference. These invisible rays are passing straight through our entire world entirely unharmed. Next up, catching cosmic rays at home, the cloud chamber. Okay, so if they're completely invisible and ghost right through us, how can we actually prove they exist without, a multi-billion-dollar particle accelerator? Believe it or not, you can build a scientific trap right at home. It's called a cloud chamber. The original idea came from a Scottish physicist named C.T.R. Wilson, who actually won the 1927 Nobel Prize for it, by the way. And the setup is beautifully simple. First, you soak some absorbent cotton with ethanol, put it over the mouth of a glass beaker. Then cover the top tight with plastic wrap and seal it up with a rubber band. Slap that beaker onto a bed of dry ice to rapidly cool it down. Finally, turn off the lights, get the room pitch black, and shine a flashlight directly into the vapor cloud forming inside. The payoff for your little home stakeout happens in the dark. If you watch that vapor cloud really closely in the flashlight beam, bam! Suddenly, you'll see a distinct, bright flash. It looks like a little white line shooting right across the mist. That line is the actual physical track left behind by a cosmic ray as it zips through the beaker. You are literally watching the invisible footprint of a space particle. How cool is that? Which brings us to solar vs galactic origins. Where do they come from? All right, now that we've actually trapped one and seen its footprint, we gotta ask, where in the vast universe are these things coming from? Well, it turns out they hail from two very distinct neighborhoods. First, we have solar cosmic rays. These guys are born right next door in our own sun. They're the fast commuters, reaching Earth just a few hours after they're formed. But then, on the flip side, we have galactic cosmic rays. These originate far outside our solar system, born in the violently explosive remnants of supernovas. Because they come from such deep space, they've been traveling for over 10 million years before finally hitting Earth. Imagine these particles getting ejected from a supernova and hurling through the freezing vacuum of space at nearly the speed of light. They're crossing these unimaginable distances, traveling for 10 million years, just to ultimately crash into the top of our atmosphere and eventually rain down onto your desk. Talk about the ultimate long commute. But here's the kicker. The particle that leaves the supernova isn't exactly the same one that hits your desk. When these primary cosmic rays, which are mostly just highly energetic protons, slam into the Earth's atmosphere, they shatter. It's basically a cosmic billiard break. They decay into this massive shower of secondary cosmic rays. It's these secondary particles, smaller subatomic fragments like pions, muons, gamma rays, and electrons, that actually survive the trip down to the Earth's surface. Let's get into the high energy paradox. Why aren't we vaporized? So think about this. We've got particles born in exploding stars, traveling at the speed of light, shattering our atmosphere and passing right through our bodies. Just how dangerous are they? To really grasp their power, let's set a quick baseline for energy. Take a familiar, everyday example. A common fluorescent light bulb you probably have in your kitchen or office right now. Inside that tube, atoms emit extra energy in the form of light, and that energy is equal to exactly 2 electron volts, or eV. Okay, brace yourselves for this one. By comparison, a single, microscopic, 1/1,000,000th of a millimeter cosmic ray particle carries an astronomical energy of 1 billion electron volts. Yeah, you heard that right, 1 billion eV, all packed into a single, practically invisible speck. You can totally understand the sheer terror of that realization, right? 2 eV for a bright light bulb versus 1 billion eV for a single microscopic space particle. If all that energy were to actually hit us in a concentrated, meaningful way, we'd get a massive, potentially lethal shock. It sounds absolutely terrifying. So why aren't we vaporized? Why don't we even feel them? Well, here's the paradox, and it makes total sense when you think about it this way. Yes, their individual energy is off the charts, but their total number relative to the size of our planet is incredibly small. Earth is gigantic, and the actual density of these particles is teeny-weeny. It's just like the source material says. Worrying about them down here is like thinking only one single raindrop could solve a global water shortage. Our atmosphere acts as this amazing, impenetrable shield, spreading them out and rendering them completely harmless to life, at least as long as we stay on the ground. But that brings us to a final, pretty provocative thought. We are perfectly safe sitting at our desks, sipping our coffee, while this invisible bombardment just harmlessly showers over us. But what happens when we leave the safety of our planet? Once we step outside our protective atmosphere, these billion electron volt particles stop being some foreign abstract mystery and become a very real, very severe threat to our astronauts. As we look to the future, the ultimate question really is, How on earth will humanity conquer this invisible barrier so we can safely explore deep space? That, my friends, is a mystery for our next explainer. Keep learning, keep questioning, and thanks for hanging out with me today.